There are only two hard things in computer science: cache invalidation and naming things. And I completely agree with this statement, especially with the first one. Because whenever you're designing complex systems like this one, where you have a lot of components connected to each other and presumably a high amount of users, we're talking about millions here, you want to make sure that your users get the best experience, because every extra second counts and costs your business money. So this is where caching comes into play, so that you can reduce the latency and optimize your architecture. So in this video, you're gonna learn everything you need to know about backend caching and how it fits into such complex system architectures. So this is going to be our outline for this video. First, we're going to take a look at some use cases and discuss why you would even need to consider adding caching to your system. Then we're going to take a look at some cache invalidation strategies, because as we mentioned before, invalidating the cache is one of the most difficult things when it comes to caching. And then we're going to talk about caching eviction policies. So invalidation strategies answers the question on how to invalidate your cache, while eviction policies answer the question on when to invalidate your cache, all right? Because invalidating the cache is important due to the reason that your data in the cache might get stale and your users might see stale data from the cache if you never invalidate your cache or clean it up. And then we're also going to talk about how to implement caching, or rather see how to implement caching. I'm going to use an example of Node.js with Redis and build a simple API and use caching there. And then we are going to talk about when not to use caching, because this is a very important point that a lot of people miss, and people add caching on every system even if it doesn't require any caching, and it would be well off without any caching, right? So imagine we have a small app with the API. So it's a server app. So imagine it's a Node app and we have a database, doesn't matter which. And we make some requests to the database to fetch some data from it, right? So let's say we have this query: select everything from users. We just want to get the users data from the users table. And now whenever we have a cache in between, the cool thing about it is that you can retrieve the same data from the cache if it exists in a cache, meaning this extra request to the database is not needed anymore. We can get the same data from the cache. So as you can see, it obviously reduces the latency because we get rid of one extra request. It also reduces the load on the database because there is no querying of the database. So database is just still running still. And we also save on network cost, because as you know, if you are running an infrastructure which is big and serving millions of users, every network request costs you money. So let's talk about types of caches by a level, because this is also quite interesting. So we have client-side caching, all right? Client-side caching is meant to be, for example, like your mobile app or a web browser. And I have an interesting video talking about that, specifically HTTP caching. So take a look at it if you want to learn about client-side caching. It's also very important for web developers. We also have CDN caching, which kind of goes hand in hand because you're serving the assets from the CDN, which is the best case scenario, and I mean the static assets. And we also have web server caching. You can also cache some requests on the web server level. For example, you make a request to your Node application and it returns the data without even going to another cache. It has its own cache like Varnish. And we also have database caching, because if you didn't know, databases like MySQL or Mongo have a built-in database caching, and it doesn't perform that well. That's why we always need something extra like an application caching. So in this video, application caching is what we're going to focus on, and it is actually the thing that concerns us the most as developers, because it's the most important layer and most powerful layer of caching for us. So let's also talk about types of caches by design. We have a global cache. Let's imagine we have an application cluster. So we have 3 nodes of Node.js servers, and we have one shared cache which communicates with us, so with the servers and with the database, aka the storage. But we also have a different schema here where every microservice can communicate to different node cache node, And this is called a distributed cache because let's say node 1 would be the primary cache and node 2 and 3 would be the replicas. So this basically allows you to optimize your architecture by having multiple nodes of caching. So going back, you don't rely only on one instance of the shared cache, but multiple. This obviously makes your system faster, but it comes with an extra overhead, like syncing the replica nodes 2 and 3 with a node 1, which is the primary. And as you can see down below, it says a cache cluster. So this is what we call a cache cluster. A typical architecture on an AWS side, because AWS is the cloud provider that I've used the most, and I think you too, would look something like this. So we have a load balancer, obviously. By the way, I also have a video on load balancers, which goes deep into them and talks about what algorithms load balancers use. So check it out if you're interested. But we also have an autoscaling group, which is, let's say, EC2 instances. Those are just servers, and they are communicating with an extra layer called Elasticache cluster. So this is the caching cluster that we talked about. As you can see on the right, we have a Redis primary cache, and on the left we have a read replica, which communicates with the primary, which can communicate with a standby database or the primary database, because you can also have replicas not only on the cache level, but also on the data. So caching strategies and invalidation. As we said, invalidation is very important, but for that, we also need to know about strategies of how we cache things. So first of all, let's talk about the write around cache, which is the quite popular, one of the two most popular strategies. It's also called cache aside or lazy loading, and I'm going to explain why. So let's take a look at the client here, right? The client makes a request to the storage and gets the data. But with the cache, what we're going to do in this case is, first of all, instead of making a request to the storage, well, a client in this case is a web server, right? In this scenario, it is a client. So what we're going to do is first try to read the data from the cache. If the data is in the cache, we return it to the client, and everything's good. If we try to read the data from the cache and the data is not in the cache, then the cache tells us that, hey, it's empty. Then we know that we need to make a request to the storage and get it from there, okay? And every time, so how do you actually update the cache? Well, every time we make a write request to the storage, we know that we also need to update the cache. So we do it at the same time. All right, so let's talk about this. It's called a reactive approach, first of all. So the good thing about that is that the cache stays slim and only contains data that it really needs, meaning that you update the cache only when you update the database. So you don't always update the cache. And it's quite straightforward in implementation, and it's pretty much used by default by most caching providers. The con is that cache gets filled only after a cache miss, meaning three trips, because you first need to request this data from the cache, and after this cache says that the data is not there, then you need to make a request to the database, and then you need to make another request to the cache to update it, right? Otherwise, how does the data get into the cache? Well, there is another caching strategy which is also very popular. It's called write through cache, and as you can see, the client makes a request, wants to fetch the data, and first we make a request to the cache. If the data is in the cache, we obviously return it. If the data is not in the cache, we write it to the storage. But the cool thing here is that if the data is not in the cache, it automatically gets updated on the way. So it sits right in the middle, and it doesn't matter if it's in the cache or not. As soon as we make a write request, meaning updating the database, the cache also gets updated. And this is pretty cool because first of all, it's called a proactive approach because we do it on our own, like actively updating the cache instead of asking the database for the data and then updating the cache. So the good thing about it is that it's well synced with the database, resulting in fewer reads of the database, obviously because we update the cache quite often, meaning every time we write. And the downside is that the infrequently requested data is also written to the cache. So why is it a problem? First of all, it's going to result in a bigger cache, and it's going to get filled with data that we don't really need to store in the cache. And application caches are usually stored in the memory, so in the RAM, random access memory. So as you can imagine, they are not that big as the disk space to be able to store such large amounts of information. And you normally implement caching when you have repeating requests. Let's say you have Instagram, and Instagram has a lot of user profiles, right? But 99% of those profiles don't get queried that often compared to celebrities' accounts. Let's say Justin Bieber. Justin Bieber's account gets queried pretty much every second. So it would make sense to cache his account for users that are requesting his account compared to my account, which gets requested, let's say, once a week or so. So if you were implementing a cache through algorithm, my account is also going to end up in the cache, which is not good. We don't need that. So that's the downside of the write through cache. But we also have a write back cache. What it is basically just simply gives us an asynchronicity. Yeah, I think I spelled this word right. So we're going to deal with the cache, just like in a write-through cache, but the writing to the database is performed asynchronously. So we are having some delay here. First of all, the downside is that the cache and the storage, meaning the database, can get out of sync somehow if we have multiple nodes, and it's difficult to manage it. Well, these kind of strategies are not enough, unfortunately, because there are some edge cases that are not covered in here. First of all, let's say we are asking for the user 123, which is Justin Bieber, from the cache, and the cache gives us this data, right? Everything's cool. But what if we have another server app which updates the database without talking to our cache? So it updates the database from the side, and our cache does not know that the database has been updated. So it updates the user 123, it changes its value to JB, like the initials of Justin Bieber, but our cache still stored this data for the user 123 as Justin Bieber. So every time our first server app, this one, makes a request, wants to get the data for user 123, it's going to get the stale data, right? And we also have another use case when cache just goes down for 1 or 2 seconds. Let's say there was an error and it's restarting. So this can also lead to inconsistencies because we're going to update the user 123 as JB. The cache is not going to see that. The database is going to get updated, and the cache still has the stale value when it's up and running again, right? That's not good. We're going to take a look at that and at some mitigation strategies. But first of all, let's talk about eviction policies, which is important to keep our cache and database in sync. So first of all, how do you get rid of the stale data in your database? Well, there's an algorithm for it called least recently used, or LRU cache. It's very famous, for example, in your mobile phones. Whenever you open multiple applications, let's say you open 20 applications, but obviously your phone's RAM cannot keep 20 applications like in the active state, so it's going to put them in a sleeping state. But how does it know which ones to put there? It's going to put the least recently used ones there, so the ones that you opened the first and didn't use for half a day, for example. So let's say we have 3 entities in our cache. Username 1 with 10 hits, let's say within an hour. Username 2 with 16 hits. Username 3 with 155 hits. You can take these usernames as application names if you were talking about your smartphone, right? And then what LRU does, it simply rearranges them. So username is gonna get to the first place, username 2 is gonna be on the second place, and username 1 with the least hits becomes a candidate for eviction. And as soon as we have a new username, let's say username 4 with, let's say, 11 hits, username 1 gets kicked out from the cache. This is how the LRU cache works. We also have some other algorithms like least frequently used cache. So least recently used cache is going to work within a specific time frame, while least frequently used cache is going to have a specific count for the usage. And we also have last in, first out, means the new application or the new username comes in, the first one, the old one goes out immediately. And we have random replacement, meaning if we have a new entity in our cache, we select one random entity and delete one of them. which is not so optimal in the case of users. So we still have this problem, right? What if the cache goes down and we update our database and it's still and the cache, whenever the cache is on again, it still serves us stale data, because least recently used cache does not help us in this case. Well, there are some strategies. First of all, you can set a time to live to eventually self-clean up your cache. So let's say your time to live for your cache is 1 day, meaning that every entity that has been added to your cache gets automatically removed by midnight. This is going to make sure that your cache is up to date and fresh all the time. We also have a lazy read repair, meaning that we can set such a strategy that every time we read from the database, for example, in the case of a set aside cache, we randomly pick requests that are, even if it's still in the cache, we're still going to read it from the database as well and update the cache. And this is done like random. And we also have some background processes. If you're using Redis, for example, you can use the scan operation, which is going to work as a cron job in your background and sync items with your cache, between your cache and the database. And now let's take a look at the implementation, as I told you. So we can have a Node.js application like this. So it's basically an Express app which uses Axio and Redis, and it's pretty straightforward. We set up the Redis here. So we're connecting to Redis server on this port. Here we have the Redis client assigned here, some error handling, okay, and we connect to Redis. And we have one route. So we are going to fetch some to-dos from the to-dos API. And what you can pass here is basically an ID for a to-do, and it's going to call this controller get to-do data. This controller basically takes the to-do ID, and we also have this cache, or this flag is cached or not, just to be able to see if this is coming from the cache or not. And we're going to have a try and catch. So we're going to first imagine this is a set aside, because by default Redis uses a set aside caching strategy. So we're going to ask the cache if it has a data for this ID. If it does have, then we parse it and we are going to return it for here. And of course we are going to say is cached, meaning that we're returning it from the cache. So from the cache is going to be true. Otherwise, we don't have it in the cache, right? Then we have to make an actual request of the API. And then we are also going to update our cache, because it's a set aside cache, and we're going to call this JSON stringify to turn the result into a string, because Redis works with key value pairs where value is a string, all right? And this is our fetch API data, which is being called here in case if the data is not in the cache. And we're simply going to call this JSON placeholder and get the to-do ID, all right? Very simple. So let's see how it's gonna work. I have 3 terminals. And in this terminal, I have a Redis instance running. So it's a Docker image running Redis server. And I'm actually going to run it again, I think. Yep, like this. So ready to accept connections. So our Docker image or container for Redis is running. And here I would like to start the server. So I'm going to, oh, by the way, let me show you the file structure. I simply have an index.js, and in package.json, what I have here is, as I told you, Axios, Express, and Redis installed, and nothing else. And of course, the type module so that I can use imports like this. So let's start the application. I'm going to write node index.js, and app is listening on port 3000. So what we're going to do is we're going to call this URL with a curl. Let's say I want to pass a different ID. I want to pass ID 42. So let's see what we got back. So from cache false, because we literally went to the API because the data was not in the cache. So as it says, request sent to the API, not to the cache. And this is the data that we got here. User ID 3, ID 42, title, blah, blah, blah. So why don't we call it again? Let's call it again from cache true. And on the second try, let's call it again, third try, fourth try, we are now getting it from the cache, because the first time it wasn't on the cache and we added it to our cache here. So we set it to the cache, in the cache. And now all the subsequent requests are coming from the cache. Now we talked about eviction policies and time to live, right? To live. And Redis gives us this option to specify these options. So first of all, we're going to say EX, and this is the time in seconds that you can assign for every item to live. For example, I would say, let's say 1000. No, I would say just 120. So 2 minutes to live. And you also have another option called inix, which is a Boolean, and it tells the Redis that only update the cache if the key is not there. So if we have the key, don't override it. Only update it if we don't have it. All right. So another cool thing that we have here is the Redis CLI. So let's run it. I think I need npx for this. So let me do like this. And I connect it to the Redis server, right? And now I can basically check what's inside my cache. So I'm going to do get 42, and 42 is simply the ID, because in here on line 38, Redis set is basically a key and value pair. So the key was the ID that I basically called before, and I do get 42, and it gives me the string that it has saved. And if I delete it again without waiting for the deletion policy, as soon as I make another request, let me first exit it, and I'm going to curl it again. As you can see, again, it's not in the cache because it got deleted, and let's call it again, and now it is in the cache. So this is how a simple example of a Redis cache would work. Obviously, in complex architectures, you would have multiple instances of this cache, and you have replicas and so. So as you saw, it's very easy to implement caching when it comes to the code. Existing solutions work very well, especially Redis, which I would really recommend. But you also have Memcache, we have Varnish, which is a web server level cache. You also have Node cache, which is also an in-memory cache specifically for Node, but obviously it doesn't have that many features as Redis. And last but not least, let's talk about when you shouldn't use a cache. First of all, if you added a cache and you see no differences between when you have a cache and you don't have a cache, you probably don't need a cache because you don't need this extra layer, right? Obviously. And the second thing is when you have high randomness of requests. Let's say it's not an Instagram application where you have determined user profiles, but you have some kind of a live stream with random comments, right? You can have so many comments on the live stream and they're all random, and you don't know which comment can be accessed. If somebody wants to answer to this comment, which comment can be accessed more frequently than other. So if you can't determine which entity should probably be cached or not, it means your data is random and you shouldn't cache anything. And again, I have a typo here, but frequently updated data, for example, like comments from the stream, don't need to be updated because that's going to be too much overhead to keep your cache and your database in sync. All right, so this was it. I hope I covered everything. If you still have any questions, please let me know down below in the comments, and make sure you subscribe to the channel to be able to see more videos like this when they're coming out. Thank you very much, and see you in the next one.